current with the current density J equal to 4 rho AZ.
J equal to, say that again?
4 rho AZ.
Amps per meter squared.
Per centimeter squared.
Oh.
Rows and centimeters.
Wait a second. Is J amps per centimeter squared?
Yes.
Oh. All right, go ahead.
And looking for the internal inductance per unit length of the wire.
Okay, what's the radius of the wire?
The 2 centimeters.
A is 2 centimeters?
Yes.
So, the whole idea is, the way we're going to calculate this is using the energy formulation. We're going to calculate the energy density. Then once we have that, we'll integrate the energy density over the internal, the internal volume of a 1 meter long piece of wire, and set that equal to 1/2 Li squared. Y'all follow me on this, class? So before we do anything, I'm going to change this J into amps per meter squared. That means that's 4, in this case, 4 rho, and it would be, if this is amps per centimeter squared, I would multiply by 10 to the 4th, and then I would have amps per meter squared. Now, I'm assuming rho is measured in meters. That's the way it's almost always have to be. And if you do this, y'all follow me on this? Because a centimeter is 10 to the minus 2 meters, right? So if you have centimeters squared, then you would have to multiply the top and bottom. Well, really, if you just think of, you multiply what? Wait a second, did I do that?
I believe so.
Yeah, that's right. It would be 10 to the 4th, because centimeters is a 1/100th of a meter. 1 over that squared would be 1/10,000, so it would be 10 to the 4th. All right. Now that I have that, the next thing I'm going to do is get the magnetic field internal to the wire, and I'm going to look right down the axis. This is a pretty good problem. If I go right down the axis, this is X, this is Y. This is going to be the radius of the wire A. Now I know that J is actually coming out of this thing. It's everywhere it's coming out, and it's cylindrically symmetric. Do y'all follow me on this? Get an idea. I'm trying to cut that piece of really wire in half and just look down there. Now I know if I come out a distance rho inside the wire and I integrate H dot dl around that closed loop, that has to be equal to the current penetrating the actual surface area that the loop is the perimeter of. Do y'all follow me on this? So over here, I have J, I'll just put it down, it would be J dot ds. What's nice is I don't even bother with this integral usually, because I know H dot dl, assuming it's cylindrically symmetric, it's just H feet times the perimeter, right? And that would be 2 pi rho. Do y'all follow me on that, class? So this is going to be 2 pi rho H feet on that side. Now over here, I put down the actual current density. It's 4 rho times 10 to the 4th amps per meter squared, and it's in the AZ direction. Now I need that dotted in with the differential surface, right? And if you look at this differential surface here that I'm showing you has to have a AZ component. Do y'all follow me? Because it has to be perpendicular to the plane it's cut from. So it's in the AZ direction. Then the differentials would be in the radial direction would be d rho, and then in the azimuthal direction would be rho d phi. Do y'all follow me? Because that's the wiper on length. Think of that right there. So that's going to be times rho d phi. So this is rho times d rho. I'm just changing the order, times d phi az. Now we put the limits on here. Well, we want h phi anywhere inside, right? From 0 to a. So if you look at this, the az's go away for sure. when I'm doing my row integration, it's gonna be technically 0 to row, and then I note that I should prime that, right? To be mathematically accurate, right? Because you can't integrate anything. Your variables inside, this is called the kernel of integration, can't be associated with the limits of the integral. So we just put a prime there to indicate that. You with me on this? It doesn't really, if you're an engineer, you know, I've been in engineering meetings, conferences all over. Most of the time, they don't even bother with that. Just telling you that. Now for phi, where do you go from phi? 0 to 2 pi. Okay, now I've got this one. Let me go ahead and just go through it down here. I have 2 pi rho h phi here equal to, and now I'm gonna have 4 comes out front. Then I get 2 pi when I integrate d phi. I get times 10 to the 4th here. And now when I integrate rho prime, d rho prime, I get rho prime squared over 2. I put it in rho, so now I have rho squared over 2 here. I'm only doing that so you see all the steps. You asked me about this. This is a good problem because it's really using what? Ampere's law to get the H field. That becomes the cornerstone of solving this, right? And you have to know how to do this stuff. On final exams, these type of problems come a lot. I mean, this type of problem where you have to understand Ampere's law to get the final result. All right, now when I take a look at this, I'm just going to erase the 2. Yeah.
Would that be rho cubed over 3?
Did I say is? Oh, I'm sorry. You're right. There's rho prime, my bad. You caught me on that. It would be, and I was wrong. This is rho cubed over 3. I'm being casual with this one. You're right. It's going to be rho cubed over 3. My bad. And stop me if I make a mistake. My neck is hurting. All right. So I'm going to get rid of the 2 pi's. Everybody. Then after that, I'm going to get rid of one of those rows. So really this is going to be 4/3 times 10 to the 4th. Rho squared would be h phi in terms of just magnitude. And that's the only thing I need. Do you all agree with that part, everyone? Okay. Now how do I get the energy density? That's the next part. It's 1/2 mu h squared, right? Magnitude of h squared. Do you all agree with me there? It's important you see this, right? All right, so that means the energy density is 1/2, just mu. There's h over there. Now I square it. I get 4/3 times 10 to the 4th squared. And then I get times rho to the 4th, right? And that would be, the units of this would be joules per meter cubed. Agreed? Now we calculate the total amount of energy. That's the energy density inside the wire going from 0 to 1 meters in length. Because we're going to do this per meter. So now, let me do it over here. But this should be, and Dr. Whitmer's book probably has this exact same steps. I don't remember, you can do this, it's tricky with flux linkage, but you'd be a fool to do it with flux linkage. If they have a variable current density like this, find the H field and set it equal to the energy density, find the energy density, and then do the energy density interval. So now, I come down to this. 1/2 L, or 1/2 Li squared, that would be the total current that's flowing in that. And this is going to be the self-inductance or internal inductance per meter, would be equal to the integral, it's a triple integral technically, of the energy density, and I'm going to just put it down this way, times the volume. It's got to be integrated over the entire volume inside a wire of length 1 meter. Y'all follow me on that? So it's just this. You're going to take the section L equals 1 meter, and you're going to integrate out to A, and A happens to be 2 centimeters, right? Okay. So now you do it. That means technically it's a triple integral. Thankfully for the dz integral, it just goes from 0 to 1. The energy density is 1/2 mu times 4 pi, or 4/3 times 10 to the 4th squared times rho to the 4th Now, I need a differential unit of volume in here. So when we talk about differential unit of volume, you're really talking about the differential surface I had times dz. Do you all follow me on this? Right? So the differential volume would be simply what? Well, it would be rho d phi if you want to do it this way, then it's d rho, then it's dz. The order makes no difference what order you put them in. Now remember, the limits on this are hard, right? This is it's a specific volume that we defined. It's not arbitrary. So here, when I go for phi, that goes from 0 to 2 pi. Everybody should see that, right? Can you all see it in the back there? All right. The rho integral goes from where to where? Guys, 0 to a, where a is 2 centimeters, right? And I'll just leave that a 2 centimeters. And when I talk about the z integral, 0 to 1. Now I'll just leave it as 1. You can make it h, but no need to make it 1. Anytime you got an arbitrary value, choose 1. You can't lose. Because then you don't have to divide it out. All right, now that's the integral, so let's see what happens here. The first part, I can see the 2 pi, I'll take all these constants out in front first. I got 1/2 mu 4/3 times 10 to the 4th squared. Then, all right, when I integrate d phi, I get phi from 0 to 2 pi is just multiplying this by 2 pi, correct? Now I'm going to do the d rho integration, but I have to take care that I count all the rows, account for them. I got rho to the 4th and rho here, which means that rho to the 5th, right? Rho to the 5th integrated is going to be rho to the 6 over 6, correct? Everyone? Evaluated from 0 to a, so I have a to the 6th over 6. And then my, let's see, yeah, the dz integral goes away. So that has to be equal to 1/2 Li squared. What's the last thing I need to solve this class?
I.
How do I get I here, Ashley, right? Integrate J, and we'll do that over here. So to get I, we're going to integrate. It's a double integral. J, which was, what was that, 4 rho times 10 to the 4th, right? AZ dotted, and here it's going to be, it can be rho d phi, and then d rho AZ. Here, to get total, the value, phi goes from 0 to 2 pi, and rho goes from 0 to a. Correct, class? All right, let's see here. Now I have I equal, that's a 4. So I got 4 times 10 to the 4th. Then I integrate d phi from 0 to 2 pi, so it's times 2 pi. And then the dot product az dot az is 1. And then I integrate rho squared d rho, which would be rho cubed or a cubed over 3 on this side. And that would be I over here. Do y'all agree with that? All right, let me just finish this up the way I would do it normally. I take a look at what I can get rid of all the time. I'm going to get rid of the 1/2 right off the bat. Okay. Now I can say I'm going to divide by I squared. So if that's I, I'm going to put down I squared here. I squared would be equal to 4 times 10 to the 4th over 3 squared times 2 pi squared, and that would be a to the 6th, right? sure, right? Okay, now if I take that and divide it into here, I get L, and that would be the internal inductance per meter. And that's gonna be 4 pi over 3, or I'm sorry, 4 times 10 to the 4 over 3 squared, 2 pi squared, and 8 to the 6th, right? I hope I didn't miss anything. Do y'all follow me on this, class? Okay. Obviously you see the 8 to the 6th, go ahead. Y'all agree with this, class? This is a bookkeeping problem at this point. Just making sure I account for it. I see the A's cancel, so I'm gonna cancel them. Next, I got 4/3 times 10 to the 4th squared, 4/3 times, wait a second, isn't this 4th here?
Yeah.
My bad. 4/3 times 10 to the 4th, these cancel, so I get rid of those. Get rid of one of the 2 pi's, right? And then I got a 6 down here, so this is, looks like it's mu over 12 pi. And that would be henries per meter. Is that the answer?
Yeah.
Class?
It's just left the hop in there, but you.
What's that?
They left the hop in there while you integrated over 1.
Yeah, but they divide that out. That's right, that's right.
Yeah, that's right.
It should be right.
Yeah, they plugged in for you because they gave you a material, but other than that.
Now, here's the one thing, all right? What, if you think about this, what is the internal inductance of a wire if it's uniformly distributed? We did that last time. It's mu over 8 pi, right? This one's over 12 pi, so this is a little less, and it's caused by that gradient of current. The current is not linear, I mean, it's not a constant. It has a change to it. And this is just a problem that Wentworth came up with on his own. All right, any other questions? That's a good problem though, because it really shows you how you have to use Ampere's law to get H, then you have to get the energy density, then you have to get the total current to complete the entire thing. You get the inductance, the internal inductance. Other questions? No. Okay, you had a test. Well, how many had a test? About half the class looks like had an exam. A lot of times when I was in school, where you were, Fridays would be the deadline for weekly homeworks and projects. I don't know why, but they always made you turn it in, like, in class, like, into class, and they would have that, and I mean, that used to cause a lot of late Thursday nights, or all-nighters. But these days, I don't even know if homework's collected anymore in many classes. I used to collect homework. Now I realize the way to hold people accountable is to make them understand the material so that they can take a quiz every week. And I've had a lot more success than they doing it that way. Okay, so today, any other questions before I go? We're going to cover magnetic circuits. How many have had magnetic circuits before? How many have had gross? Let's try that.
Yeah.
There we go. Now, those people should have had magnetic circuits at some, because I know he does this every time he teaches now. So what are magnetic circuits? Frankly, they're equivalent of electric circuits only with magnetic materials. And what I like to do is draw an analogy. Everybody knows this symbol for a battery, right? That's a potential, it's really a pressure, an electrical pressure, it's voltage, right? This is the electric equivalent, I'll just put E, and this would be the magnetic equivalent of a force. And it would be simply a bunch of turns here, and you would have where each one of these turns has a current I, and it is simply Ni. The symbol that they use is this. They'll just have this, it'll be plus or minus, and they'll have Ni This is the magnetic force. It's the number of turns times the current per turn. And this is called a magnetomotive force. Technically, this is the EMF, the electromotive force. This is the magnetomotive force. Don't worry about this right now. I'll show you how it works. Everybody knows what a voltage source is, right? So think of turns times current as a magnetic force equivalent to the voltage in terms of what it does. Next, everybody knows that you have something, a lump parameter called a resistor that you're familiar with, right? Well, resistor, if they're a linear device, or just, if you talk about constant cross-section, a resistor is equal to the length of a piece of material divided by the cross-sectional area of that material, and then divided by sigma. This would be the DC value. So if you had a block of material like this, and it had a length L, and current was going to flow down the axis this way, and it had a cross-sectional area right here of A, and it had a conductivity sigma, that would be the resistance. We've covered that. Y'all with me on this class? How many got that part for resistance? All right. The magnetic equivalent of this would be for iron, like something with a very high mu, constant cross-section, so the flux is contained within, is this. It's same symbol. It's actually a script R, and it's proportional to the length, inversely proportional to A, but now it's divided by mu, not sigma. So you might think of the permittivity, or permeability, pardon me, of metal is like the conductivity of really most conducting materials like carbon and stuff. Y'all with me on that? Or copper, something like that. So now in the simplest sense, if I have a magnetic circuit, and this is the most basic magnetic circuit, like such, and I have N turns, and there's a current I flowing through there, and I say that the bar's cross-section is A, and the total length around this bar is some capital L, all right? And the bar here, I'm trying to show you an iron core for a transformer, if you understand. And the total actual, inside this bar, it has some permeability mu, which is much, much, much greater than mu naught, or mu relative, you should say, is much, much greater than 1. Then I can say the electrical circuit that's equivalent to that, or I should say the electrical analog in terms of components, would be a voltage here, Ni, and a simple bar reluctance that is associated with that entire path around there. And the reluctance value would just be L over mu A. Now, I'm making it simple, but you all see what I'm doing here, right? So anytime you think about an electrical circuit where you have a voltage and a resistor, like so, the next thing you can get is the current, right? That's just V over R, correct, class? All right, well, the equivalent to magnetic current is called flux. So when we take a look here, the magnetic flux, which is in Webers, is simply equal to the magnetic voltage, Ni, divided by the total reluctance. And that, and the units of this are Webers, but it's like electric current. The parallel is exact, by the way. All right, y'all with me so far? All right, so we've covered the magnetic voltage, if you will, the MMF, it's Ni. We've talked about the reluctance of any kind of closed magnetic path. By the way, the reason they use iron core for transformers, all the magnetic flux basically is contained within it because it's a low magnetic resistance path. All right, that's the reason they do. Now we get down to this point. This is in Webers, right? Now, over here we had I, but the next thing we can get, not from a lump element model, but from this model right here, is we can get the current density, can't we? We can say if we know I, J would be equal to I over A in terms of its magnitude. Do y'all agree with that? Right? Just follow the logic on this. So we come over here, we can get the equivalent to that. If we take the magnetic flux in Webers and we divide it by the cross-sectional area that it's flowing through, it would be the cross-sectional area of the bar. Now, I made this bar very easy to understand. Constant cross-section, it's got one total path length to worry about. But it could be different stages. You could have a bar with a different cross-section or different material. There could be an air gap. All these things would basically make the problem a little more complicated because you would have to account for the magnetic resistances associated with each point. But nevertheless, the same basic phenomena goes on. Now, if you have flux over area, that's meters squared. What is that, the symbol we use for this? What is, that's right, Webers per meter squared is the B field, right? So that B field right there is like the current density over here. The parallel is exact. Y'all with me? Now, next, let's go back here for a second. If you have J, do you remember when you did these calculations of resistance? You would assume current, right? Then you would get J, assume it uniformly distributed. After you got J, what was the next thing if we're going to get resistance? E. Do y'all remember that? We would say E was equal to J over sigma. Y'all remember doing that stuff, right? All right, so if you take B and you divide it by mu, what do you get? H. You get H, amps per meter, right? So H is like the E field. Think about it. The E field is what? Volts per meter? Here, H is amps per meter. Same type of units. One associated with electric, the other magnetic phenomenon. Got me on this? And it's not hard to see this. Once you see the parallels, this whole thing falls apart. Okay, I got H. I got all this stuff, right? I could get magnetic energy density as 1/2 mu H squared. Electric energy density is 1/2 epsilon E squared. All right, I can go ahead and draw some more parallels, but these are the essential. So if I have this, and this is one thing kids miss, and I don't think Gross covers this, but he might. So this is my circuit, my magnetic circuit that I've got. And now I want to know the inductance of that circuit. So how would you get the inductance? Let me ask you this. When you think about inductance, you can think about the energy approach, right? Or what other approach? You can say it's the total flux going through a single turn, right? Times the number of turns, flux linkage. Do y'all agree with that, class? So isn't this basically a turns kind of problem? All the flux is flowing around that closed loop and going through each turn. Do y'all agree with this? Now this would be the self-inductance. If I put another set of coils over here, then we get the mutual, but this would be self. If we want that inductance, and this would be the inductance of this bar, what we'd do is take the flux, this, flux flowing times the number of turns, and divide it by the current creating it. Now, do you all follow my train of thought here? The flux is the total flux flowing through one complete turn. I multiply by the number of turns, now I have the flux linking all those turns, and if I divide by the current I creating that flux, now I have the inductance. Do you all see the thought process? People miss this. All right, so now let me go ahead and just put in the values here. So the flux is Ni over reluctance, Then that is times I, right? I'm sorry, times N, pardon me, times N. And then it's divided by I. Now when you're calculating inductance, it's not a function of I, unless it's a nonlinear material. And everything we do in here is linear. You all follow me how the I's cancel in this one? So I's are gone. And what you see is what? That's proportional to N squared over the reluctance of the core. You all see that? How many see that right there? All right, that's important, because that gives you a good feel for inductance. N squared is the number of turns on the core, and if I know the reluctance of that core, I got a real good idea what the inductance is, self-inductance. This would be the inductance of the primary. Got a question for you. Suppose I wanted the inductance of the secondary. And what I mean by that is call this N1 here, and now I'm going to put N2 over here turns, but I'm not connecting them to anything, so there's no current flowing. Now, do I know the flux that's actually penetrating those cores? Yeah, I know the flux is the flux times N2 would be the amount, right? It's caused by what? The primary, right? So I divide by I1 of the primary, and now I have the mutual. Did y'all follow me on this one, class? The only thing different is now I don't multiply this by N1. What I end up doing is what? Or this would be N2 here, right? This would be N2, and this would be N1. So it's the primary times secondary terms instead of just primary squared. Y'all follow me on that? And these are handy little things to know when you're dealing with primarily transformer design. How many have had this kind of stuff with transformers? You've had basically an understanding of this from Gross, I think, probably. Right? It's important. Okay, got that done. Now, I went through that fairly quick, which I was happy about. We can also talk about the magnetic forces in lifting objects. Now, y'all know what I'm talking about, electromagnets, or if you've ever gone to a dump or anything like that, where they've taken cars, they have these electromagnets that lift them. And you can figure out the electromotive force. I think I may wait until Monday to do this part, because there's a few other things I have to talk about. But did you have electromagnetic lifting force when you had Gross? Did he go through that or not? Well, it's not hard to do. Usually, I'm not going to have time today. I got to give you time for the quiz. But I want to just say one thing. I'll do that on Monday. I want to do this in a way that's meaningful to you, because most of the time you don't want to just memorize formulas. You want to see it applied to something. If you're going to lift a car, how much current would it take on a standard type of electromagnet? That's a good question to actually lift it, because at least it'll give you an idea of what it takes to do that. And it depends on the number of terms, as you might guess, but we'll get to that on Monday. Final thing I'm going to do today before your quiz is just tell you where we're going next, and that is into chapter 5. We're about done with chapter 4. I think we've covered all the topics in chapter 4. So for chapter 5, this is time-varying electromagnetic fields. I want to tell you one other thing that I hope I have time to do. I look forward to doing this. I'm going to actually show you how to calculate the velocity you're going to get, approximate velocity, for something like a coil or a railgun. Railgun just has two currents. I mean, it's a differential current where the actual short cross of two current elements causes or allows the force to be activated and pushes it. A coil gun is just a whole lot of coils. They put some ferrous in there and they taper the current so it will cause a net magnetic force that will launch it out. I'm going to go through that because, frankly, whenever I did that, students enjoyed it. And then they went on YouTube and they had fun with it. Some kids built things like coil guns and rail guns, and I always got a kick out of that because they were very proud of themselves for building a weapon based on something I learned in class. Anyway, so now, to do that, you have to appreciate time-varying magnetic fields. That's my hook to get you interested in some of this. You want to build a cannon? Here's how. But you have to understand this. The laws change a little. In electrostatics, you remember that if you took the curl of the E field, well, maybe you don't remember, it was 0. But here, we're going to have two laws that change. You're going to have curl of H is gonna be, before it was just equal to J. Y'all remember that? Curl H equals J is the point form of Ampere's law. Now there's a second term added. It's plus the partial of D with respect to T. Some people are gonna wonder, how do you know that? These are based on measurements. Lots of measured data where these mathematical laws become evident. They compare all the things. That's how they get these things, from measurements. These are not in stone somewhere in the Bible. They are based on measured experimental data. That's the first. That is Ampere's law. The second is Michael Faraday's law of induction, and that's curl of E is equal to minus dB dt. Now those two sets of laws govern all electromagnetic phenomena in the universe. They're never ever inconsistent. They're self-consistent. If you look at this, J is equal to sigma E. That's for materials with conduction, right? D is equal to epsilon E, and B is equal to mu H. So those are the things that couple every parameter over there. Do y'all follow me on this? Now, one other thing that happens if you look at this right here. Now remember, this is a law you're gonna have to take on faith. It just is based on bajillions of measurements, all right, where we figured out how nature works. If I take the divergence, write this down, divergence of curl of H, it is by definition zero. By definition, mathematical definition is zero. That means if I take divergence of J plus the partial with respect to T of divergence of B, it's equal to zero as well. This is called the continuity equation. Are you familiar with this equation at all? Have you heard of continuity? Well, you have, you didn't know it. Remember Kirchhoff's current law? Whatever flows into a junction flows out of the junction, right? Well, this one's slightly different. It means whatever flows into the junction, which would be divergence of J, is no longer zero because this is time varying. It's equal to anything accumulated. So with Kirchhoff's current law, whatever flows into the junction current-wise flows out of the junction current-wise, or results in a charge buildup would be Q, and that would be a capacitive effect. So if I look here, the next thing I do is simplify this a little. I have that 0 is equal to divergence of J plus d dt of divergence of D. What is the divergence of D equal to in terms of something observable? Charge density. Remember, div D is equal to rho V, the volume charge density? How many remember that? Or at least now it's ringing bells, right? Divergence of D is equal to rho V, the volume charge density. That's important. Now it's a continuity equation with div D being replaced by the charge density. What that means is if I give you J right here, and I wanted the charge density here, I would take divergence of J to this side and integrate it with respect to time, right? And now I'd have the charge, I would have rho V. Simply said, it would be minus the integral of divergence of J, right there, and it would be dt from some minus infinity to t would be equal to rho V. These are just things you have to understand the linkage there. There's one other thing that happens. If I replace J with sigma E, right? And then, if you take a look at this, I can replace E, well, let me go ahead and do it one at a time. If I come down here, I'm going to go ahead and start with 0 is equal to divergence of J plus the partial with respect to T of rho V. Now I come down here, I have 0 equals divergence of sigma E, that's J, plus the partial with respect to T of rho V. Y'all see what I'm doing here? I just replaced J with sigma E. Everybody with me? Now, what is E with respect to D? D over epsilon. Y'all see this? So now I come over here and I say, well, I have 0 is equal to the divergence of sigma d over epsilon plus d dt of rho v. And I can take the sigma and epsilon out in front. So I have sigma over epsilon divergence of d plus the rho v dt. Why do you think I put that divergence of d there? Anybody? Exactly. Now we're talking, right? Here's the assumption, all right? It's important you see this. You can't do this operation. I can't take sigma and epsilon out in front unless they're constants. So if that sigma value or epsilon varied over the material, like as a function of distance, then that divergence would cause those things to change the divergence from what I'm doing right now. You all follow me on that, class? But if they're constant, this happens. And I can just do this. Now, if you look at that, what is that? Isn't that a first order linear differential equation? Because it's equal to 0, right? Anytime you have a first order linear differential equation, you know basically the solution to this. This looks like dy dt plus ay equals 0. The solution is what? Y is equal to some y naught e to the minus what? T over a, right? And let me just put it down here. This solution to this one is rho v of t to some rho v 0. That's the value at t equals 0 times e to the minus t over tau, and tau is equal to epsilon over sigma. And this is this is really, I've had sigma over epsilon here, but if you take rho v over epsilon over sigma, that would be tau, and that's the general solution to that. Now you can take a look at that, because frankly, the way they usually write this equation is rho v over tau plus the rho v dt equals 0, and then the solution is rho v is equal to rho v 0 e to the minus t over tau. Now that's a simple exponential decay. Isn't that akin to an RC circuit's decay? You charge it, then let the resistor and capacitor be connected. It discharges at an exponential rate. If you look at this, tau itself is akin to R times C. Just take a look. You know C is proportional to epsilon, right? R is proportional to 1 over sigma. It's RC. It's the same exact form of the time constant. Okay. So that's my. I'll give you some homework, and on Monday we'll do magnetics, magnetic lifting, and we'll start going down this route. And I promise you, if you're interested in doing something on making a magnetic, I hope I don't get in trouble. I will give you some of the stuff you need without supplying weapons. All right, do me a favor, spread out. Take your phones out, put them on the desk, you know, move people around, but don't be offended, we move people all the time, and we're all. It's closed, we're closed, now, can you take your phones out, just put them face down?